Today you will be able to find limits approaching infinity for various types of functions. We're going to start off with a theorem. If r is a positive rational number, so any number that's not negative, and c is any real number, both positive or negative, doesn't matter, then the limit as x approaches infinity of c divided by x to the power of r equals 0. This also works for when x is less than 0, such as if x is approaching negative infinity, then some number divided by x equals 0 as well. Let's see why this works using an example. All right. Given this example here, the limit as x approaches infinity of 4 plus 3 over x, we are going to numerically find what the limit is as we go out towards infinity. To do that, we're going to use different x values. We're going to use 10 to the power of 0, 10 to the power of 1, 10 squared, which if you're wondering, this is 1, 10, 100, 1,000, 10,000, and then 100,000. Would you agree that as we go along here, the x value is getting bigger and bigger? We're going to use the table in our calculator to see what would happen. So I've entered in the equation. I made sure to set my table to ask because I have very specific values I want to use. And now I'm going to go to the table and start putting things in. So when we've gone 1 over, we find that the answer is 7. The y value is 7. When we go 10 over, we find that the answer is 4.3. So with just two numbers, it looks like we're getting smaller and smaller. 100 over, 4.03, 1,000 over, 4.003, continuing on. Notice that the number is getting smaller and smaller and smaller. Till finally we get to just 4. Here's why. This is the part that's being divided by these numbers as they get bigger and bigger. Notice that the limit equals 4, which means that as a really, really, really big number divides a smaller number, it basically just cancels out and equals 0. So the only thing you're left with is this 4. That's why the overall limit is 4. We're going to find the limit of these next 3 examples as x approaches infinity for this following function. Notice in A that we were going to be dividing the function by x. So let's write down what this should be. The limit as x approaches infinity of 5x squared minus 3x plus 7 over x. What you want to do is divide this into 3 separate fractions. So the limit as x approaches infinity of 5x squared over x minus 3x over x plus 7 over x. Remember, we're going to simplify, so we get the limit as x approaches infinity of 5x minus 3 plus 7 over x. According to the theorem above, if we plug infinity in down here, that's going to be a number divided by a really, really, really big number. So this just goes to 0. The 3, of course, is still just a 3. But if we were to plug infinity in here for this x, we're going to have a really, really, really big number. We can't even label it, so we'll just call that infinity minus 3 plus 0. And honestly, if you subtract 3 from infinity, you're still just going to have infinity. So that is your overall limit. In the next equation, we're going to have the limit as x approaches infinity of 5x squared minus 3x plus 7 all over x squared. Again, we're going to divide this into 3 separate fractions. So the limit as x approaches infinity of 5x squared over x squared minus 3x over x squared plus 7 over x squared. Simplify it down. So the limit as x approaches infinity of 5 minus 3 over x plus 7 over x squared. According to the theorem above, a number divided by a really, really, really big number cancels out to just 0. Same thing over here. So we're left with the limit equaling 5. Try the last one on your own. This leads us directly into functions with radicals. To find a limit at infinity of a function that has a radical, we have to use the fact that for when x is greater than 0, x can be rewritten as the square root of x squared. Here's why. Think of it like this. You can rewrite 2 as the square root of 4. You can rewrite 3 as the square root of 9. That's all they've done here. The square root of x squared is x. This is going to come in handy in the next example. For when x is less than 0, x can be rewritten as negative square root of x squared. This is because when you take the square root of a number, remember you're left with both a positive and a negative answer. The positive and the negative answer. We're going to be using this, the fact that x is the same thing as the square root of x squared, to divide both the numerator and the denominator and find the limit. So look at the first example. The limit as x approaches negative infinity of x over the square root of x squared plus 1. I first want to point out that this is as x goes to negative infinity. So we need to use this rule here for when x is less than 0. This means that x is the same thing as negative square root of x squared. I just want to keep that in mind, so I'm going to bubble it off to the side so we don't lose it. Rewrite this. We have the limit as x approaches negative infinity of x over x divided by the square root of x squared plus 1 divided by negative square root of x squared. All we did here is multiply the top and the bottom by a special form of 1. Remember that x over the square root of x squared is the same thing. This can just be rewritten as x over x. So all I did is multiply the top and the bottom by a special form of 1. The reason I did the bottom with the square root of x squared is so that I can use my radical rules and I can combine these two radicals into one simple radical. So if we rewrite this, we have the limit as x approaches negative infinity of 1 up top over the square root, the negative square root, just pull this negative out front, of x squared plus 1 being divided by x squared. Notice, I went from 2 radicals to just 1. Now I can simplify the inside of the square root. Going to have the limit as x approaches negative infinity of 1 over the square root of x squared over x squared plus 1 over x squared. This will reduce to 1. So I'll have the limit as x approaches negative infinity of 1 over the negative square root of 1 plus 1 over x squared. And then according to the theorem, if we were to plug this number in, a number divided by a really, really, really large or a really, really, really small number cancels out to just 0. And I'm left with 1 over negative square root of 1, which equals 1 over negative 1, which is just 1. So the limit of this function is negative 1. You could use a calculator to numerically or graphically prove this as well. I want you to try the second one on your own. I can tell you that the final answer is 3. See if you can figure it out. Let's move on. Infinite limits at infinity are observed when a function does not approach a finite value as x increases or decreases. Right, of course that makes sense. Basically, you're going to have to use long division to rewrite the improper rational function as the sum of a polynomial and a rational function. So, in case you have forgotten, long division, we are going to divide this by that. So write a division sign. We have 2x squared minus 4x on the inside. On the outside, we're going to have x plus 1. The goal is, what do I need to multiply with this to make it look like that? To get this to that, I need a 2 and another x. So if I multiply this out, remember to distribute to both of them, I get 2x squared plus 2x. You're going to be subtracting these. These will cancel. And negative 4 minus 2 is negative 6x. Again, the goal is to make this look like this. What do I need to multiply this by to make it look like a negative 6x? Well, I need a negative 6. Distribute to both of them. I get negative 6x minus 6. I'm going to subtract these fractions. These will cancel. And I have 0 minus negative 6, which is just a positive 6. I can't multiply anything to this in order to get it to be just a 6. So I have a remainder of 6 over x plus 1. The reason we did this is so we could rewrite this entire equation as the limit as x approaches infinity of 2x minus 6 plus 6 over x plus 1. If we were to plug our infinity in, this would be 2 times a really, really big number, giving us just infinity, minus 6. And then this would be 6 over a really, really big number, which just cancels out to 0. Infinity minus any numbers is still going to be super, super large. So our final answer is just going to be positive infinity. I want you to try this last example on your own. I'll give you a hint. You're going to have to put all of this over 1 and then rationalize the numerator. Your final answer will be 0. Good luck.